Okay, so let's see. We're going to go off of that, and we're going to go back to HDMI laptop. So one of the things I just want to re-emphasize, we discussed it last day, I want to re-emphasize this idea that the main traits of the binomial distribution is that you have a fixed number of trials. What you're interested in counting is the number of outcomes of one type. There are two types of outcomes, which is why we call it binomial. And we call one of the types of outcomes the successes, because those are the ones that we count, and the ones that we are automatically the n minus x types are the failures. Again, you know, what's the success? It's just whatever we decide we are counting in those n trials. The trials must be independent of one another. In other words, what does it mean for a trial to be independent of one another? It means that the outcome on one trial does not affect the outcome on another. And the kinds of things that we're used to that kind of scenario is flipping coins and rolling multiple dice, okay, where the outcome on one die doesn't affect the outcome on the other die, etc. So some things are what I call physically independent, okay, or structurally independent there. So we have this independence. We also get that with earned problems when we sample with replacement. To a large extent, we get it when we deal with large populations, when we actually sample without replacement, because even though technically the probabilities change very slightly as we select things from the population is so large the probabilities don't change to any substantial extent. Okay, so we're not usually too concerned about things that the probability changes in the 5th, 8th, 10th decimal place. So again, the trials are independent, and the probability of a success on any trial is constant. Okay, and that is our P. So you got to recognize all those situations. If all of those situations hold, or all of those assumptions hold, then the number of successes when we draw n trials, it must follow a binomial distribution. That's just the derivation from elementary probability, which we did last class. Okay, so all of this, we defined just for convenience, some books don't bother defining a Q equals 1 minus P. They just always write 1 minus P. But it just makes things a little bit simpler if you actually just say, well, Q is going to be the probability of a failure, which is just 1 minus the probability of a success. And so here's a term we haven't used really before, is the idea of a parameter. And the idea is, what is a parameter? It is a number that characterizes a distribution. And so what we need to characterize for a binomial distribution is the number of trials that we're going to have. For example, how many times are you going to flip the coin? And P is going to be the probability of a success. So if it's a fair coin, if we're talking about flipping a coin, P is 0.5, right? The probability of a success and a failure are equal, but there's nothing that says we couldn't have a P other than 0.5. Maybe it's a bias coin. Maybe we're rolling a die and we say, we roll a die 20 times. What's the probability that the number 2 shows up X times, 3 times, or something like that, right? And there we would have a P of 1/6 for a fair die. And again, just re-emphasizing the idea that the trials are independent, and it is our classic sample with replacement distribution, but again, if we have a really large population that we're sampling without replacement from, we'll usually use a binomial as a useful approximation. Now, what we're going to try here is a simulation of a binomial distribution, and we're going to try to play something called the quincunx. Let's see if we can get this little thing to link through there, and yes, we have it. And works where you're right. Install. No, I don't want that. Just go. And let's just see why. Let's just see if I can get that to stay on the screen. Okay, so this is also called a Galton board. And the idea is that there's a board and it's got pegs in it. And the ball gets dropped onto the first peg, and such that it has a 50-50 chance if, in fact, we start off with a probability of 50% going left or right. And it continues to bounce down, and each time it has a 50-50 chance as to whether it goes left or right on the current split of 50-50. And this is it's running simulations of size 6, and what it's counting here is how many times it gets no balls landing in this bin here, and how many times it gets 1 ball, and how many times it gets 2 balls, and so on up to the number of times it gets 6 balls going this way. In other words, this is going, well, on my side, right. In other words, how many times does it bounce off the pegs to the right 6 times? That's what we're looking at. Each ball is going through 6 trials. 6 trials, and what we're counting is the number of times it is going to the right. So if it comes down on the left side every time, we have a value of 0. If it comes down to the left 5 times, but then once to the right, we're going to get an x value of 1. So every ball is a trial with n equals 6 and p equals 0.5. Now I'm going to reset this thing. I'm going to restart, and I'm going to change the value of p to something else. How about 75%? So now it's got a 75% chance of going to the right and only a 25% chance of going left. And just a second, I have to see this. We can speed it up. Speed, speed, speed. Let's go. Boing, boing, boing. Boing, boing. Let's really go wild. So to get a value of 6, again, it has to bounce to the right side with each of the 6 pegs that it encounters. And to get a value of 0, it's got to bounce left all 6 times, and then there's various times in between. And we can let that go and go even faster. Okay. There's top speed, top speed. Okay, so one of the things we notice here when p is equal to 0.75 is that the probabilities are heavily shifted towards the right side, while what we're getting is a long tail coming out the left side. And what we call this data, you might think that this data, because the probabilities are all pushed over that way, that is skewed to the right, but that would be wrong. We actually call this distribution skewed to the left, because the skew is like a skewer, you know, something you put things on a barbecue, and that is the long tail, and the tail is coming out on the left side. Now let's just reset this and switch that to, I'm gonna restart. It doesn't want to restart for me. Okay, I want to move this to restart. Okay, I want 70, well, about may not be able to get there, 75% to the left. Okay, restart with that. Okay, so now the probability of a failure, again, going to the right is considered a success on the way it's counting x here. You notice that we're getting the same distribution, but it's like the mirror image of the previous one, right? And the only time we get a perfectly symmetrical one, which I don't know if I can reset this one nicely enough. Let's see if I can hit. Okay, well, I'm going to be slightly off of 0.5 here because the slider is hard to get 0.5 exactly. But when p is 0.5, the distribution will be exactly symmetrical. The true probability distribution is exactly symmetrical, and with our simulations, we're going to expect the distribution to be roughly symmetrical about the middle, which is the mean, and right now you see some variability. It doesn't look all that symmetrical yet, but you got to let these things run a while for sort of the properties of symmetry to emerge nicely. We'll try to get you some extra things on that. So anyhow, you can play the quincunx.
Gary, does anything interesting happen if you make the size big?
I can make the size big.
Happens?
Absolutely. Oh, absolutely. Yes.
Does it look cool or anything?
What would you like? Give me a size.
I want it as big as possible. You know, bigger is better.
Oh, bigger is better. Bigger is better. How big will they let you make it? They'll let you make it to 14. Okay, let's restart it.
Woohoo!
Woohoo!
You might have to scroll down a little.
Maybe. Let's get it in there. It's going at top speed, but notice this.
Maybe we can leave it in the background. We can come back to it later in the class. See if
we can do that.
If any cool pictures have come up.
Sure. Okay, so now we're going to go, we'll just minimize this one for now and go back to this. And, okay, so we've already discussed this, that the random variable can take on values from 0, the integer values from 0 to n, and that's n plus 1 values because you've got 1 to n is n values, but then we've got the 0, so that's an n plus 1. Mihai has discussed expected value, and it does take some mathematics. It's not a trivial proof, but when you sum up x times p of x for all x in a binomial distribution, you can prove that this comes out to a very simple n times p. Well, let's kind of think about why that kind of makes sense. You know, you flip a coin 10 times, it's a fair coin. On average, how many heads would you expect to get? You'd expect to get 5 heads and 5 tails. If I roll the die 300 times, how many times, and x is the number of 2's I get, well, the probability of getting a 2 is 1 out of 6. And so with 300 trials, I would expect 1/6 of those 300s to be 2's. 1/6 of 300 is, it's 50. And that's kind of what I would expect for each of the other numbers as well, but we're counting the number of 2's. So the expected value is actually rather logical for a binomial distribution. Deriving it is not a trivial exercise. It's actually a mathematically kind of tricky exercise. So we derive the ideas that any value of n and p, you can get these p of x values. We have derived that function last day on paper. Hope you were here. If you weren't here, make sure you get notes from somebody who you will owe big favors to. Maybe they won't charge you a lot of money, but nonetheless. Now, you can calculate all these, but there are ways of getting these values relatively easy with computer software. There's books that have tables of this, but they're for limited values of n and p. We're not going to worry about tables. What we want to do is look at some of the software that allows you to calculate these values of n and p. And we're going to have you install the program R on your computer, okay? So we're not doing a lot of R in this course, but we're going to do a little bit, okay? R is a huge statistical software program that is free to everybody all the time in the world, and wherever you go, whatever you do, you will be able to install it free. So what I want to do next is just show you a little bit about installing R on your computer. And just a sec, let's just gotta do that, and then I gotta go to, I want to go here, and then I'm gonna open some sort of tab, and then I'm gonna, yes, I'm gonna do this. And so what I'm gonna do is Google the letter R. Okay, just Google the letter R. Who wants to give me Raptors Republic? I don't want Raptors Republic, I just want the letter R. And what's the first thing that comes up? The R Project for Statistical Computing. So the fact that that's the very first thing that comes up on Google when you just when you search for R suggests that it's pretty big. It is big. Okay. And then you will see stuff there such as R 4.4.1 for Windows, but you're not stuck with Windows. You will go in there and they will give you the various things to download R. And the first thing you get is to choose your preferred CRAN mirror, which is basically where you're going to download it from. And Canada's got a few sites, so Toronto used to be one of them, but now University of Waterloo's taken over that one. So Waterloo's close, but it doesn't really matter where you download from, okay? So you're going to install that, and then it's going to ask you, would you like to install for Linux, for a Mac, or for Windows? Okay, and it installs very easily, and they put out new versions every so often. You want to keep your versions up to date, and you can just, you don't have to mess around with the earlier versions. You can just install the latest version as it comes along. So this is what we call base R. In class, I will use base R. In some of you might discover that there's something called R Studio, which is nice. It's got some nice features to it. It also has some issues that sometimes comes up with it, but R Studio is simply a nice wrapper around the regular R software package, and lots of you will end up using R Studio. They both work equally well. Well, they both work. R Studio is simply implementing R, so with a couple extra things gussied up. It's proprietary software, so it's not my first choice of things, but there's a free version, and so lots of people like that. So anyhow, you can install R, and so once we've installed R, what are we going to do with this? Well, let me go back to my slides now. And let's get back here. And I've still got that. Just a sec. I have to get in there. We got that. Blah blah blah. Install the program R on your computer. And so we're going to use R to calculate some binomial probabilities, both individual and cumulative probabilities. And so I will be posting these slides. I wouldn't worry about making notes. And we're also going to do a few simulations with R. So here's an example we're going to try to work through. Very simple one. Binomial distribution with parameters n equals 10 and p equals 0.5. In other words, this is equivalent to flipping a fair coin 10 times, and you are going to count the number of heads. And so what's the probability that x is less than or equal to 4? In other words, you have no more than 4 heads. What's the probability x is actually equal to 4? X is greater than or equal to 4. X is greater than 4. X is less than 4. One of the things to watch, because I will tell you this because this is a very common mistake on tests, is the translation of words, okay? So x is less than or equal to 4 is equivalent to saying x is no more than 4. Whereas x is less than 4, x is less than 4 is 4 is not included, right? You've got to be careful on this. What does it mean to say x is at least 4? That's going to be at least 4. Is 4 included in at least 4? Yes, it is. So that's a greater than or equal to 4. Whereas if it says x is more than 4 or exceeds 4 or something like that, then that's an x is greater than 4. So there's a bunch of things we want to get. So we're going to do this with R in a little bit, but here's another way online. There's all kinds of online calculators, and one of the kind of cool ones for tables is this one called StatTrek. And I have gone to StatTrek, but that has not gone to StatTrek, which means that I have disengaged the game. Okay, so now I'm going to have to, I am engaged. So let's see what they do. Okay, probability of success on a trial. Let's put in 0.5. And number of trials, we're going to do 10. And then number of successes, x, is 4. And then I am going to go calculate. And it calculated everything I wanted. Just like that. Faster than you can do it in your head. Okay? Okay? Now, these probabilities, can you work them out using your equation? The equation we had, the probability mass function? Yes. You should be able to verify all of these. Now, the easy one to verify, of course, is this one. Okay, how are you going to verify that? Well, it's going to be 10 choose 4, 0.5 to the 4th, 0.5 to the 6th. The 0.5 to the 4th times 0.5 to the 6th will just be 0.5 to the 10th. But the point is you should be able to just calculate that one by hand, just verify that it is doing everything correct. And for some of the others, you got a little extra work. This is a relatively simple one to calculate because that's going to be the probability x equals 0 plus the probability x equals 1 plus the probability x equals 2 plus the probability x equals 3. Probability x equals 4 is not included. So we can work out a few of those. Okay, and again, you can play out with things, you know. Some of the things are, you know, if I had n equals 37 and p is 0.23, well, this is kind of like a pain to calculate for some number like, say, 11, but it can do it pretty fast. Okay. We can do the same things with R, and we're going to go to R next. And this is working. Yes, it's working. Okay. So I'm happy. But now it's frozen. No. Okay. So the R functions for probability distributions, I'll give you a little general introduction here, is that there are 4 key functions in R for binomial distributions, but we're just going to worry about the dbinom, the pbinom, and the rbinom function. We're going to ignore the Q functions for now. And these functions exist for a very wide range of special probability distributions. We're gonna discuss a couple more probability distributions, but as you go into further years, you're gonna see lots of other kinds of probability distributions. And if you were to Google special probability distributions in R, you will find there's a big pile of them. So the key ones we want to focus on first is the difference between what we call the D function and the P function. So between dbinom and pbinom. So the dbinom is going to give you the probability that the random variable x takes on a particular value of x, and the qbinom function is a cumulative probability. It's going to be the probability that the random variable takes on a value less than or equal to x. Okay, so if we were to put in, you know, an n equals 10 and a p equals 0.5, and we want the probability x equals 4, we would use dbinom, but if we want the probability that x is less than or equal to 4, we would use the pbinom. I've often kind of regretted the choice that R used for their functions, whether it's dbinom, pbinom, or whatever. I kind of wish the p's had been used for individual probabilities and that they had used a c for the cumulative, but they didn't. And so I can't tell them to go change their software, because they're not going to listen to me. Okay, so the programmers that did it this way, and we just have to adapt. So these are really cool functions coming up, and this will be something that we can have some interesting fun with, is what's called the R functions, the random number generations or random values for a particular distribution, and so we'll look at those. So I'm going to bring up R in a moment, but first of all I'm going to just try to give you some slides that we can refer back to, and then we'll check it live on R. So if I use dbinom, remember dbinom is individual probabilities, and it has this syntax called, you put your x value in, then you put your size. That size is our little n. And we'll see later on that we can get a little confused with that. And then the probability is the p-value, the probability of a success. So here's an example, and what I would like you to do is also, you know, just on your own, go on your calculator, verify the result with the probability mass function equation. So if I ask for dbinom with an x value of 4, a size of 10, so that's saying that I'm going to do 10 trials, and the probability of a success on each trial is going to be 0.5, it will pop back and say the answer is 0.2050781. And we saw this number before because we also generated this with the StatTrek software. I didn't actually have to type the size equals, prob equals thing. As long as we remember what goes where, I could have just done 410 0.5 and it would know what to do. Okay, so you don't have to type the size equals, the prob equals thing if you remember where everything is. So individual probabilities. Any questions there so far? Individual probabilities, everybody good? Okay. So pbinom, remember these are cumulative probabilities. And our syntax is, well, it looks just like the syntax for dbinom, and it is. So here's a couple of examples. If I do pbinom 4, size equals 10, probability equals 0.5, I get 0.3769531. Okay, and again, that is, we've seen that number before. Maybe to round it off to a few more decimal places. But again, this is not the probability x equals 4, it's the probability that x is less than or equal to 4. So this is the probability x equals 0, plus the probability x equals 1, plus the probability x equals 2, plus the probability x equals 3, plus the probability x equals 4. Again, I don't need to specify all of these size equals, probability equals. If I just say pbinom 410 0.5, it gives us our answers. Now the next one is more fun when we actually do it on a on the R itself, but we'll outline it for the time. So again, I emphasize that these are cumulative probabilities. So the last one we got to discuss on the functions are the R functions, and well, I'm going to give the syntax, then we're going to go to R. rbinom. Okay, so this one has a kind of a strange syntax because it has something called n equals, but that's not the same as the number of trials that we have. The number of trials is size. The n refers to, and again, it's kind of unfortunate, but that's what they've specified. This is going to be the number of times you want to do a binomial trial of a particular number of trials. We'll see what we mean by that. So I'm going to just say, note there's a potential confusion between our two uses of n. And I can't help that because that's what they decided to call things. And we also use n for number of trials when we do our probability experiment here. So here's a couple of examples. If I say rbinom n equals 6, size equals 10, probability equals 0.5, I don't know if any of you are running R already, you could be. When I ran this, I got the numbers 364725. If you run it, I'll bet you don't get those numbers, right? So what is that telling us? This said, okay, so this is equivalent to flipping a coin 10 times, and I got 3 heads that time. And then I flipped the coin another 10 times. And this time I got 6 heads. And then I flipped the coin 10 more times, and this time I got 4 heads. 10 times I got 7 heads. I flipped another 10, this time I only got 2 heads. 8 tails. Ooh, that seems fishy. And there's one, I flipped it 10 times and I got my expected value of 5. But I didn't get it very often. Okay, and we could skip the size equals and prob equals, and oh my goodness, it's broken. It gave us different numbers. Because it's just generating a new set of random results. Okay, so nothing's broken. Okay, so let's now, well, let's go to R next. So what are these values? Well, you get the same values. Let's go to R next. Go to R. Go to R. Go to R. Go away. Go away. Okay. Go away. God, this is problematic at times. Okay, I'm going to start up some R here. Let's see, 4.41. I actually have a lot of R versions on here because I kind of collect them. I want to collect the whole set, which would be a really stupid thing to do. No, I can't. There's actually a reason I keep old versions, and I'll just increase the font a little bit here. GUI preferences. Let's go up to, well, I could go up to 14, I think, on this one without breaking anything. Okay. So I've started up my R, and the current version 4.41, and they always come up with some weird title like this one's called Race for Your Life. People often ask how to get started on R quickly. There's no ends of tutorials up on the internet and that kind of thing. Generally, they give you much more than we want for now, but you're going to learn it over the future courses and that kind of thing. We'll give you a little bit, but you can just use it as a calculator, just, you know, couple things, you know, 2 plus 5. It's very convenient when you can't find your calculator, you know. 63 divided by 567, you know. You want to square a number. There's a couple ways of squaring. This is the carets, one of those ways. Another way is double asterisks. Ooh, what do you mean? Oh, I hit something by accident. Okay, so that's another way of squaring things, and you know, you can take square roots. Square roots, how do you take a square root? Well, there's a couple ways. One way is 64 to the power 0.5. That works. Or I could have done square root of 64. So there's a bunch of special functions defined. You can lots of different functions. But what we want to do is go to our binom situation. So let's just go through those again. We had dbinom, and we said pick an x, pick number of trials, pick a probability. This is exactly the ones we worked out before. We got that. Whereas if we did pbinom.
Whoa, how did you type that so fast?
This is because I'm a lightning typist.
Oh, amazing.
Yeah, it's amazing. So I think what Mihai is getting at is how did I get to the pbinom so quickly?
Yeah.
Yeah. So you can go up, go down. Up, down, up and down arrows, okay? So what I did with the dbinom, I went to there and I switched it to a pbinom, and then I got that, okay? And you can play with, different values in there. So now I want to do the rbinoms. And any questions there so far? Oh, here's another little thing you might, maybe I'll leave this one for a bit. Do I want to do that for a bit? Come back to that one. Could generate a whole vector of probabilities.
Draw a graph of some of these things?
We can draw a graph.
How do you draw a graph in R here?
We can draw a graph in R, but it's got a bunch of commands to get a nice one.
Maybe we don't.
We'll come back to doing a couple nice graphs on this. Okay. Okay, I want to do rbinom. Rbinom. So we did one. We said we just said do 6 with 10 and 0.5. Not even the same values I had before. Outrageous. Okay, let's just go up and make sure that I did that right. What's going on? What's going on? Of course, it's generating its values fresh each time, right? So there is a bit of a trick. Let's suppose you wanted to hold on to a set of random numbers, and could I do that? Well, I could by assigning it another variable. So I might decide to something like call it sample 1 is assigned rbinom 610 0.5, and so it's going to generate a sample that I can't see right away, but once I generate it, it holds on to it, and if I went up and asked for that, it holds that sample. Okay, so that's another little, I won't call it exactly a trick. Now the thing is, we just looked at 6. Flipped a coin. We flipped a coin 10 times. We did that experiment over 6 times, and I'm going to do a sample 2 because I want to get more ambitious than just running 2 of them. What if I did 100,000 of them? Oh, that's dangerous. Maybe 100,000. I could do 100,000, but let's do 1,000 to start, because some of you might be tempted to look at sample 2, and if I did 100,000, you'll find it scrolls for a long time on your screen. So let's just do 1,000, and if you actually looked at that, you would have that. Whoa! And well, that's a lot of numbers, but if I were to take that and give a table on that, it counts how many times it got no heads, 13 heads, or sorry, 1 head, 2 heads, 3 heads, etc. There's how many times we ended up with all heads, all tails. Okay? And you look at those numbers, you can see the binomial distribution.
What happens if you type in hist of sample 2?
Pardon?
You do hist of sample 2? I want a hist.
I can tell you what it does is it doesn't always do the histogram the way we want it to do. And so we often have to break it up.
Oh, that was
okay.
beautiful to me.
Not too bad. That one's not too bad. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 bins, you see, as opposed to 11. Okay?
Can we see the quincunx that we've been leaving running before we leave?
Pardon?
We dropped
Oh,
like
the quincunx. Yes. Where did our quincunx go? Where was I running that? I was running it somewhere. The bulletin board.
Yeah.
There it is.
Oh, I didn't run.
Huh?
I don't think it was running. I think it paused while you were gone.
It must have stopped when I was doing other things. Anyhow, wish you all a great weekend, and we'll see you Monday. See you Monday. Did you remind them about the homework?
Oh, yeah, well, I just sit down. So there's homework due Monday, basically checking if you saw the video, so make sure you check that out.